So the last talk of the day will be functional collection programming with semi-ring dictionaries, presented by Amir, Shaikhha, and co-authored by Mathieu, Huot, Jaclyn Smith, and Dan Olteanu.
Yeah. Thank you so much for the introduction. There are several things which are puzzling a bit with this presentation. First of all, it's not as exciting as the previous separation logic talks. So this is not a separation logic talk. So if you want to leave, I won't be offended now. So the other puzzling bit is that if you see it's 2022, but we are in 2023. So the story is that we didn't manage to present it last year because of visa issues. And thanks to the organizers, we have managed to squeeze it into this session now. So, and as this is the last talk, I assume that I have infinite amount of time, or maybe not. So we will see. So,
Same infinite amount of time as everyone else.
So not that much has changed since 2022. So still, we are surrounded by a lot of data. So here on this beautiful figure, you can see that at every single minute, how much data is produced throughout the web. And most of this data are actually structured. So for example, either they are structured in terms of a graph or relational data, or matrices, which in many cases, those matrices could have many zero elements, which are referred to as sparse matrices. And actually, in the deep learning world, also now, sparse neural networks are a big thing. So they are also structured data. But data by itself doesn't matter that much. We want to extract knowledge from it. And so this is done through data science. And this is basically a high-level view of an end-to-end modern data science pipeline. So we start from this structured data, and then we perform data wrangling using databases or some Python library. And again, we further process the data, and then we convert it in form of tensor data, and then we feed in that to PyTorch or TensorFlow in order to train some machine learning model and learn some parameters. So the input data was really nicely structured. So for example, if it was relational, there were some poor guys who have invested a lot of time to create first normal form, third normal form, all these kind of fancy things that you would study in your undergraduate database course. But this structure gets lost throughout this process. So let's zoom into each of the components, intermediate components here. And if we zoom into them, we usually see that they are dealing with two types of workloads usually. So either they are database-ish workloads or they are tensor-ish or linear algebra-ish workloads. So for example, the data warehouses and these kind of things are using relational data. They issue SQL queries, and machine learning, computer vision, graph processing are issuing something inspired by linear algebra. So, but these are two completely separate worlds. So for example, the database world is relying on notations, formulations such as relational algebra or nested relational algebra, and the systems are relational database systems or a poor person's relational database system known as Panda data frame. And the linear algebra world is basically relying on linear algebra and tensor algebra and the frameworks. I don't need to mention about them. But there is such a disconnect between these two worlds. Let's try to zoom in a bit into each of these systems, the systems for each of these workloads. So in a very high level, you can think of a relational database system basically as a compiler. So it takes SQL query as the input, it parses it, it converts it into a variant of relational algebra, and then there is some engine that basically knows how to digest the expressions of relational algebra and take relational algebra data, which is basically relations, tables, and then produce the answer. And one nice thing with relational algebra is that it's an algebra. So it has some nice components such as selection, projection, aggregation, join, which are, thanks to their mathematical formulation, they enable the database system with several cool optimizations. So for example, you would be enabled with pushing selections before joins so that you create less large intermediate relations. Let's see the machine learning frameworks. Again, we see a similar architecture. So instead of getting SQL as input, they get Python, MATLAB, or R as input. And at the end of the day, after doing the parsing and all these kind of things, they produce some linear algebra expressions. And there is some library implementation of each of these linear algebra operators where whenever you feed in them with the matrix input, they're going to produce the answer. And again, linear algebra is an algebra. It provides some cool optimizations similar to what we have seen for the relational algebra. Similar, but different. So the question that we want to answer today is that can we have a unified environment? And for that, let me show you one example of an advanced optimization that some of the database systems would do. Let's consider the case that we are joining three relations and we want to compute a group by aggregate over the join of these three relations. So if we first join them and then compute the aggregate, it's going to be producing a large intermediate data. So instead, what we can do is that we can compute some partial aggregates by just joining two of the relations together and computing the aggregate of that, and then join the result of that aggregation with the other relation, and then compute the aggregate over that too. And in the linear algebra world, we realize that there is a similar optimization. Whenever we are multiplying three matrices, rather than writing a nested loop which directly tries to multiply the three matrices together, so we can instead first multiply two of the matrices and then multiply the result with the other matrix. So this optimization in the database world is known as pushing aggregates past joins. And in the linear algebra world, is known as matrix chain ordering. And here in this work, we are introducing a new DSL, or intermediate language, called Semmering Dictionary Query Language, which we claim that it's going to bring these two communities together. So let's decipher this name. So the first term is a Semmering. What is a Semmering? It's basically a set with two particular elements and two binary operators, addition and multiplication. So one of those particular elements is the identity element for the addition, and the other one is basically the identity element for multiplication. So 0 is identity for addition, and 1 is identity for multiplication. And we have a bunch of quite intuitive rules here, axioms defined for a Semmering structure. And one of the most important ones is basically the distributivity law, or the factorization rule, that connects these two operators together. And some of the examples of Semmerings are basically real number and natural number Semmerings, which are kind of obvious. Another interesting one is that whenever you have false and true, you have conjunction and disjunction corresponding to multiplication and addition. And another interesting one is basically something known as the tropical Semmering, that instead of addition, you have minimum or maximum, and instead of multiplication, you have addition. And now let's decipher the next term, which was dictionary. So what is a dictionary? A dictionary is basically a key-value pair. And what is a Semmering dictionary? It's basically a key-value pair where the value forms a Semmering. So I'm using a ring notation because I didn't know how to represent a Semmering. But the nice thing with this Semmering dictionary is that it can subsume all the existing collections that we would see in the database and linear algebra workload. So for example, in the database world, there are two different semantics for relations. One is the set semantic, and one is the bag semantic. And both of them can be represented as a dictionary. The set semantic is a dictionary to Booleans, and a bag semantic is basically a dictionary to an integer. And also, on the linear algebra board, a vector is basically a dictionary from the indices to the value. And a matrix is basically a dictionary from the pair of indices to the value. So visually, consider the following relation, and you can see that it's with the back semantic. Thus, we have the several duplicates. So you can see that A1, B1 is mapped to 2. A2, B1 is mapped to 2 again, because we have 2 occurrences of them. But the last one, A2, B2, is mapped to 1. So it's a map, it's a dictionary from the tuple to the multiplicity. And a matrix also can be represented as a dictionary from the pair of indices to the values. And here, one nice thing is that we don't need to really represent the elements of the matrix, which are the addition identity elements. So here, we don't need to represent the 0 elements. So let me show you in very high level what are the semantics of a program that is written in our language. So basically, we have a looping construct, which basically what it does is that it iterates over the key value pairs. And in the body of that, we want to specify how we should add the elements together. So here, in this case, if F is basically returning a double, basically this C++ code nicely digests what this looping is doing. Or let's, in the body also, we can have also semi-ring dictionaries, which basically what it does is that the output of that is going to be a dictionary, but at each iteration, we are updating the associated value with a given key with whatever is provided by the bound value. So some of the examples, so we can basically capture the translation of all bunch of SQL queries to that. So here we can see that whenever we have a count query, we basically need to just sum up the multiplicities together. Whenever we have a summation of a particular element, we have to just multiply that element, that attribute with its multiplicity and sum them up. And also, we can capture group by aggregates by introducing a dictionary with the group by key as its key. So this is a fancy figure that shows that, believe me, we are capturing the translation of all relational algebra operators. And similarly, we can capture the vector operator translation. So one interesting one is that whenever we are doing the element-wise product of the 2 vectors, so basically, we need to iterate over the key value pairs of one of the vectors. And we have to create a dictionary where the key is actually the index of the row of that vector. And the value is going to be the result of multiplying the value of this vector with looking up the value associated with the key from the other vector. And now, in the case of the dot product, we just don't need to create these intermediate dictionaries at all. We just are going to sum them up. And similarly, again, we have the translation for a bunch of linear algebra operators. And one interesting thing that now we have here with SDQL is that, again, because of its algebraic nature, and the fact that our looping operator has algebraic nature, we can express a bunch of well-known loop optimizations as rewrite rules on top of this language. So I'm not going to go through all the loop optimizations that we have here. I'm just going to show you one example. So let's consider this example where we are joining the elements of 2 relations R and S together, and it's an equality join, as you can see here. So one interesting thing that we can do here is that here, inside this, we can basically memoize, statically cache the definition of this function. And after this transformation, one interesting thing that we can observe is that now this part of the code is basically invariant to the outer loop. So we can apply loop invariant code motion and get it out. So what we basically did here was that we have translated nested loop join in databases to a hash join, which is actually taking from O of n2 to O of n. It's a linear algorithm. And similarly, we have also for other loop transformations, such as vertical loop fusion, horizontal loop fusion, and other kind of things, similar optimizations. And also, we can express a bunch of data layouts that are known in both the database world and sparse tensor algebra or dense tensor algebra world. And so we have also cool experiments, and the outcome of that, our experience is not that we are better than the other systems. We are actually competitive with systems that are specialized, built for a particular task. So our system is generic, but it can reproduce the same performance as what those specialized systems are doing. And so at the beginning, I said that, OK, this was for 2022. Nothing has happened. I lied a bit. So it has been 1 year. We have published more around this language. So first, we have some work on efficient query processing inspired by this language in Python that has appeared in CC. We have also done sparse tensor algebra by combining with equality saturation technique that appeared in SDQL23. And we have done also automatic differentiation for sparse tensor algebra by providing AD rules on top of this language. And also, yeah, everybody's doing machine learning. So we have also done machine learning for automatic tuning of the data structure choices here. So to conclude, we have introduced the semi-ring-based language which can subsume relational algebra, nested relational algebra, tensor algebra, and it enables optimizations both inside each of the data science components and also across the data science components. And we have shown that it's basically competitive with specialized system in the sparse tensor algebra world, analytical databases, and also hybrid workloads of doing machine learning inside database systems. So you can refer to the paper for also some proofs as well as more extensive experiments. Thank you so much.
All right, thank you. Do we have a couple of questions?
Hi, thanks for a great talk. So one thing that people want to do in linear algebra is to solve or to do, I don't know, Gaussian elimination, whatever, to solve some linear system. And one thing people sometimes want to do with a database is to find like a closure of a relation, like find paths through some graph or something. So is there some way to express that, or are you thinking about how to express that here?
Yeah, so basically there is a notion of closed semi-ring that basically just introduces the closure operator in addition to the semi-ring. So we have a section in the paper that actually explains how we can extend this language here. But the core language that we have doesn't have the support for that. Thanks for the question.
Yeah, hi. I'm one of the guys from Mars, according to you. When you said that you can support different matrix formats, do you mean that all the matrices in your equation, your system, would be of that format and you optimize? Or do you say whatever matrix comes in, I'm able to, well, or let's say the system is able to optimize the term as given for these different matrices? Because then the order of evaluation might be quite different than what you would conclude from the mathematical specification.
Yeah, so basically in this paper, SDQL23, we actually consider different types of formats, especially for sparse tensor algebra, such as CSR, CSC, and all of those things. And we show how our language can express computation on top of those formats. So we basically support those formats natively inside the language. Yeah.
So it's really awesome that you were able to do these optimizations that apply uniformly in both relational algebra and linear algebra. Obviously that has savings in terms of reducing duplication of effort, but it seems like maybe the biggest win might be if you have applications that actually use both. And so you don't have to switch between two different systems to get these benefits. Have you seen, is that a thing?
Yes, exactly. So in the experiments, so I didn't invest too much time on the experiments. So we basically here have benchmarks where you consider the end-to-end data science pipeline, where you do need to, for example, first do feature extraction with a database C workload, and then you want to train a machine learning model. Let's say, okay, for now we are supporting like regression models. And so, yeah, we express both of them in terms of this language, and then we do cross-domain optimizations.
Excellent.
Yeah.
Great. All right, so I wish OOPSLA could go on for infinite time, but all sessions must end. So thank you very much.
Thank you.